So welcome everyone again, and welcome to the first talk of this year's conference. And we will start with David telling us about AdS bulk locality from sharp CFT bounds.
Okay, great. Thanks a lot. It's really nice to be here virtually giving this talk. Given that this is a specialist audience, this talk is going to be a little bit technical. I'm going to try to dive into some of the meat of the calculations of this paper. There was a nice review talk by Leonardo and a talk about this work by Simone at Strings that are a little more of a broad overview. So you could have a look at those if you're interested. So the goal of this work is to derive effective field theory in AdS from holography. And specifically, I'll be talking about weakly coupled effective field theory and considering large N CFTs. And by weakly coupled effective field theory, I mean that the theory is weakly coupled at low energies, not necessarily at high energies. And we know that at high energies, interesting things have to happen to the structure of the theory in AdS, given that the CFT is well-defined. So the setup that I'll be considering is the one discussed by HPPS in the seminal paper now several years ago. They conjectured that if you have a CFT with a large central charge and a large delta gap. So here delta gap is the dimension of the, let's see, the lightest single trace operator with J, let's say, bigger than or equal to 3. So the lightest higher spin single trace operator. If you have a CFT with large central charge and large delta gap, then the conjecture is that the correlation functions of the CFT are predicted by a bulk Lagrangian, where the Lagrangian satisfies our intuition, is consistent with intuition from effective field theory. So specifically, the Lagrangian has a derivative expansion. And in this talk, I'm going to be talking about a CFT that contains a scalar operator and focusing on bulk scalars for simplicity. But a lot of the lessons that I talk about should be applicable to other cases. So this bulk Lagrangian should describe a scalar in AdS, and it has a derivative expansion. So we can write down a series of higher derivative terms. These are schematic. And the claim is that, well, so our intuition from effective field theory is that these higher derivative terms should be suppressed by some heavy scale in the bulk, and the guess for that heavy scale is delta gap itself. Delta gap over R AdS gives a heavy mass scale in the bulk, and we expect these higher derivative terms to be suppressed by that mass scale. And so the claim is that this scaling, this effective field theory scaling, should follow from large central charge and large delta gap. That's the conjecture. And our goal in this talk is to prove that conjecture. This is partway towards the more lofty goal of deriving AdS from holography. There are, of course, more things that you might want to do. You could be interested in multi-point interactions. You could be interested in finite temperature backgrounds, things like that. And I won't have anything to say about those. For now, I'll be focusing on these 4-point contact interactions and showing that they behave consistently with effective field theory. Okay, and
what's the numerator that you wrote there? GN?
Good, yeah, thank you. Yeah, this is Newton's constant, the bulk Newton constant. Could write it as Gn. So basically, this goes like 1 over CT. And I should say I'm happy to take questions during the talk, so please feel free to interrupt me as Joao did. Okay, good. So there's been an important lesson that's really been driven home over the last couple years from flat space, which is that this kind of effective field theory scaling, consistency with effective field theory dimensional analysis, can be derived in flat space from canonical S matrix assumptions. So if you assume the usual assumptions, causality, analyticity, and Reggie boundedness, those let you derive dispersion relations. And the interesting new development is that by studying positivity conditions on these dispersion relations, you can prove two-sided bounds on these couplings that establish EFT dimensional analysis. So the bounds have the form some number over a heavy mass scale to the appropriate power, 2n minus 2, is less than or equal to gn over g, which is less than or equal to some number over m to the 2n minus 2. So it corners these couplings to lie inside an island, an infinite set of islands for all these high derivative couplings. And this follows from positivity of dispersion relations. So this allows us to move the goalposts a little bit to make things easier. So what we will do now is try to derive dispersion relations starting from CFT axioms. So this leg of the race is already established. There's technology for going from dispersion relations using positivity and establishing EFT dimensional analysis. So our task will be to do this one. So what we'd like to do is look for CFT sum rules. That is, these sum rules are going to be equivalent to the statement of the crossing equation, but we want sum rules that become flat space dispersion relations in appropriate limits. I'll talk in more detail about what that actually means. One nice thing about this is if we succeed, we get an alternative derivation of dispersion relations that's really independent. You start by assuming CFT axioms and out pops dispersion relations in AdS. And that's really different from the usual path where you make assumptions about analyticity, the analyticity structure of the S matrix and Reggie boundedness of the S matrix. In flat space, we don't have great control over those assumptions. It's interesting that there's an alternative way to derive these dispersion relations, and maybe there are some lessons that can be learned there, moved between flat space and AdS. So once we have CFT sum rules that become dispersion relations, then we can apply flat space technology to construct positive sum rules. That is, sum rules that get positive contributions from heavy states. And that's the key thing that you need in order to get bounds on low energy EFTs. Okay, so that's the new goal. So let me start by reviewing a little bit about dispersion relations in flat space, which is what we'll be aiming for. A simple class of dispersion relations can be obtained by taking the scattering amplitude m and performing an integral over an arc at infinity. So that's what this contour integral is, with some subtraction. So we stick in powers of the Mandel sums, enough powers so that this integral over infinity is 0. And then once you do that, so you have the contour integral over infinity is 0. And then the usual thing is that you pull the contour inside so that it wraps the heavy cuts. And you also get some low energy contributions. And this gives you an equivalence, an equality between some contributions at low energy and contributions at high energy. And as an example, in the case k equals 2, you get the following equality. So the low energy contributions are here. I'll call this C2U light. So C2U is the name of the sum rule that we're looking at. So these are the low energy contributions, and they contain the Newton's constant, and then these contact interactions. So this was the coefficient of d to the 4 phi to the 4, and this was the coefficient of d to the 6 phi to the 4, and so on. And on the other side of the dispersion relation is some kind of sum over heavy states. And I'm using this angle bracket notation. So the thing that's being summed over heavy states is this combination. And I'll sometimes write it like this. And the angle brackets are a sum over masses and spins of heavy states of with some positive measure. So the nice thing about a dispersion relation in this form is whenever you have a dispersion relation, if you can take a linear combination of dispersion relations such that the stuff inside the angle brackets is positive, then it gives you some kind of constraint on the low energy data. And that's the basic mechanism for getting constraints on EFTs. I'm not going to talk in too much detail about that. Because as I said, we're going to import technology from flat space. So if you're interested in that, you could. There was a nice talk by Simone in this series a few months ago that you could look at to learn more about that. The thing I want to focus on right now are some of these properties of dispersion relations that will give us targets to aim for in considering CFT sum rules. So we're going to focus on three properties. So one property is that the contribution of heavy states to dispersion relations is proportional to an integral of the imaginary part of the amplitude. And this property we already know how to get in AdS. Simone taught us a few years ago that this means we should consider sum rules such that their heavy contribution is an integral of the double discontinuity of the 4-point function. So this part of the dictionary is clear. Another property of the dispersion relation is that it is these subtractions. So we can stick in these subtraction factors, and they do two things for us. One is that they suppress the Regge limit. So the Regge limit in this case is s goes to infinity with fixed u. And so more and more of these factors in the denominator suppress that limit, and that suppression is important for the contour integral to vanish. And at the same time, we get new contributions from the light stuff. So every time we increase the order of the pole at s equals 0, we get new contributions from light coupling constants. So we'd like to look for a similar mechanism in the case of CFT sum rules, some way to suppress the Regge limit so that we have control over the sum rule, getting the appropriate contour integral to vanish. But at the same time, we should look for this kind of seesaw effect where you suppress the Regge limit, you get more stuff from the light sector. And then the last property we'll be concerned with is what this dispersion relation measures. In this case, it's not too hard to just write down the answer from the construction of the dispersion relation. So we know that u, this Mandelstam variable u, is minus p squared, where p is the transverse momentum. So that's the momentum in the transverse d minus 2-dimensional space, capital D minus 2-dimensional space. So that means that this dispersion relation CKU is making some kind of measurement of a scattering process where we have momentum eigenstates with this particular momentum, P, in the transverse direction. And by changing P, we can change the transverse momentum. Gravitational, so positivity bounds and gravitational AFTs require considering large transverse momentum. So this is related to this construction that I won't have time to talk about too much in this talk. But this means that we're going to need to pay particular attention to finding CFT sum rules that achieve large transverse momentum, whatever the analog of that is. Okay, so there are two big question marks here. One is, what is the CFT analog of subtractions? And the other is, how do we figure out what a dispersive sum rule measures? And so that's what I'm going to talk about next.
David, can I ask a question?
Yeah, please.
Just about the general logic of this, are you assuming that the flat space theory is a limit of a family of theories in AdS?
Oh, good. Let's see. That would be the cleanest framework to work in. You imagine that you have a the cleanest framework would be to imagine you have a family of CFTs where you can take CT arbitrarily large, so that you want to take CT to be the largest thing in the game. And you can also take delta gap to be large. So you have this parametric control. So the basic example would be n equals 4 supernos.
Wait, but even in that case, are you assuming you're not, wait, are you assuming the flat space dimension same as the AdS dimension? What about the large internal space?
Okay, good. Yes, you're right. So for simplicity, I'm going to talk about that case. That's right. So I think if there is some large internal space, then the story is going to have to be modified. But I'm hopeful that that will be possible.
Okay, but sort of in almost essentially all the examples we have, there's large internal space, right?
Yes, that's true. I'm working with a toy model given to us by HPPS that is sort of the simplest setting for thinking about these ideas.
Okay.
But I mean, at this level, it's okay, right? It will be 0 modes on the S5 or close to 0. So it will just change some prefactor. I mean, Silvio and collaborators, they have bit to that this flat space limit formula with lots of coefficients and everything matches, right? So it's not like we don't know how to treat this internal space.
Yeah, also I'm not sure. In the specific case of n equals to 4, of course, we have a consistent truncation. So at 3 level, it's not going to matter, right? So for the low energy contribution at 3 level, we don't really care about the Kaluza-Klein modes.
Yeah, that's right. The bounds are not going to be optimal, but they will be correct. The other comment, what I thought you were leading to was this question about parametric families of CFTs. And what I wanted to say there is one nice thing about having a concrete sum rule is that once you've derived the sum rule, you can forget about parametric dependence of anything and just ask, where is the sum rule positive? And that will give you bounds on even theories with finite CT and finite delta gap. So the idea is to construct bounds on theories in this limit of large CT and large delta gap, and then they'll apply in a neighborhood of the limit. That's the idea.
Thanks.
So David, just to be clear, you're assuming CT to be the largest thing, and then delta gap is also large, but not as large?
Yeah, that's right.
Okay.
Good. Yeah, I probably should have written that in the first slide. Okay, great. So let's get to understanding these properties. So we'd like to write down CFT sum rules that mimic all of these 3 features. And let me first talk about getting a sum rule that whose heavy contribution is proportional to an integral of the double discontinuity. So there's a very natural way to do this, which is to consider a commutator of 2 null integrated operators. So we put these 2 operators on the same null plane. So this is the null plane here. Everywhere along these integration contours, 1 and 3 are space-like separated, and therefore their commutator vanishes. The commutator of 1 and 3 vanishing at space-like separation is basically just the statement of the crossing equation. The claim is that if we do these null integrals, it kind of pushes this statement of causality sort of to its maximal extent, to the trickiest possible region where you could study causality. And in this case, you get the most interesting bounds from doing this. This construction of doing this null integral naturally gives you the d-disk. And let me remind you why that happens. So you start with this statement that 0 is equal to the integral of this commutator here. And you split the commutator into 2 terms. So we have these 2 different orderings of the operators. And then each of the terms individually is proportional to an integral of the double discontinuity. And that's because the null integral of a single operator kills the vacuum. So in this case, we have a null integral of phi1. And so we can replace this product phi1, phi2 with a commutator because the integral of phi1 kills the vacuum. Similarly, here we have the null integral of phi3. So we can replace this product with a commutator. And so we end up with an integral of the double commutator, and that is the double discontinuity. So this is a very simple way to get a sum rule. So of course we had to have a statement that something was 0. So we have that 0 is equal to some kind of integral of d-disk. And this is the S channel d-disk and the T channel d-disk. So some linear combination of those. This particular sum rule that I've written down can be related to the Lorentzian inversion formula at negative integer spin. So another way of writing the sum rule is that if you take the 4-point function and plug it into the Lorentzian inversion formula at j equals -1, then that should be 0. And that's not an obvious statement, but it turns out to be equivalent to this statement above. Basically, what you need to do is take this statement, which is an integral over space-time, and move to cross-ratio space. And when you do that, you'll find that the kernel becomes precisely the Lorentzian inversion formula. So that's a very nice sum rule, but one problem is that this sum rule only converges if the Reggie intercept of the theory is less than -1. If it is less than -1, then we have this situation of superconvergence, where the Reggie behavior is very highly damped, and so we get a very powerful sum rule. But in general physical correlators, we don't expect that to be the case. One thing we know is that non-perturbatively, J0 is always less than or equal to 1. So that means that if we want a valid non-perturbative sum rule, we need to find a sum rule that converges in this case. And this one is not sufficient. But it does have this nice property that it is the integral of a d-disk. So that leads us to the next property, which is subtractions. So there's a very simple idea for fixing this problem, that this sum rule above only converges if J0 is less than 1, which is to just stick some extra factors into the 4-point function that damp the Reggie limit. And the simplest example of this modification is to take the 4-point function, g of u and v, and just multiply it by this factor. So to orient you, the Reggie limit here of interest in my conventions is the U-channel Reggie limit, which is z and z bar going to infinity with fixed ratio. So this combination here is something like z plus z bar minus 1 over z bar 1 minus z 1 minus z bar. And so you can see that it does indeed damp the Reggie limit, and it damps it by 3 units of spin. Basically, you just count the powers of z and z bar in this limit. And so that means that if we stick this factor into the sum rule, then instead of getting a sum rule with Reggie spin -1, we get a sum rule with Reggie spin -1 plus 3, which is 2. So this gives us our simplest spin 2 sum rule. And another property of this subtraction is this seesaw effect. So in flat space, remember, when you stick in these extra factors in the denominator, you suppress the Reggie limit, but you get new contributions from the light sector. And the same thing happens when you stick in these factors here. Let me just explain how that works. So the usual way that you get the d-disk is to consider one of these null integrals, let's say the integral over x1 plus. So we have the integral from -infinity to infinity, and there's going to be a singularity in the integral when operator 1 becomes light-like from operator 2. The way to get the d-disk is to take this contour and wrap it around the singularity. And when we do that, we get the discontinuity across this branch cut, which is what a commutator is. And in practice, the behavior near the branch cut is described by some power of x12 plus. This is a consequence of the operator product expansion. And so when we take the discontinuity across the branch cut, we get a sum of phases, which combines to give a sine factor, and then times the integral against just the positive part of the branch cut. A nice thing happens, which is that this sine factor, which came from the linear combination of phases taking the discontinuity, it has a 0 at double trace locations. That 0 survives as long as this integral is non-singular. So that's what happens in the case of the usual d-disk. You get this sine factor from one of the discontinuities, and then the other discontinuity gets you another sine factor. So you get this famous sine squared factor in the d-disk. Now, when you stick in this subtraction, then the effect of the subtraction is to stick in an extra factor. So we have this 1 over x12 plus. And basically what that does is it kills the 0 at the first double trace family. And if we were to stick in more subtraction factors, so more powers of u and v in the denominator, we would kill more zeros, and therefore we would get support on higher and higher double trace families. So this should remind you of the higher poles in S, giving you more and more light contributions. It's not obviously the same thing, but it will turn out to be the same thing for a non-obvious reason. Okay, any questions? Okay. Good. So, all right. So the general strategy then that we have so far is to take this superconvergence integrand, this double null integral of the 4-point function, and modify it by sticking in some meromorphic kernel. And the meromorphic kernel should have poles at the S and T channel OPEs. And these poles, what they do is they ensure that the new contributions from light states come from some finite number of double trace families, according to this mechanism that I just described. So the basic sum rule looks like this. We have this double integral. We have the kernel that we stuck in, and the role of the kernel is twofold. It's to suppress the Regge limit, but also give us these new contributions from light states. And the action of our sum rule on a conformal block is just given by sticking in a conformal block for the 4-point function. So this here is my notation for an S-channel conformal block. Finally, you can choose this kernel to be antisymmetric under swapping 1 and 3, and that's important to get a non-trivial sum rule in the case at hand, because we started with a commutator 1 and 3. So if we have an antisymmetric kernel, then the action of this functional on an S-channel block is the opposite to its action on a T-channel block, and so we get a non-trivial statement of the crossing equation that the sum over squared OP coefficients of the action of the functional and conformal blocks is 0. And what we're going to do to mimic a dispersion relation is split this this sum rule into 2 contributions, one from heavy states, so states with dimension bigger than delta gap, and one from light states. So basically this just collects everything else in the sum rule. And so I'll call this omega heavy, and this is minus omega light. And minus omega light equals omega heavy. That's just the statement of crossing symmetry, but in a particularly useful form. So now we're ready for the last key property of our dispersion relations that we want, which is that we want them to measure something useful. And particularly, we want to be able to measure.
Sorry, David, before you move on, just one clarification. So above what you call heavy, it's all heavy single trace. It's independent of spin, right? You're not using the fact that delta gap was defined for spin greater than 3, greater or equal to 3.
Yeah, that's right. So good. So what we can do here is let's see. So the sum is over all operators with dimension bigger than delta gap. So this statement here doesn't actually make any reference to single or double trace or anything like that. And that's important because eventually at high enough energies, you'll get to regimes where the large N expansion breaks down and you can't categorize states into single, double trace, et cetera. And we want our sum rules to still be valid in that situation. So this sum over here collects everything with dimension bigger than delta gap. The fact that that the sum rule depends on the d-disk allows us to do this separation very cleanly. So because it has double zeros on double trace operators, there's going to be like a large regime of energies where it doesn't get contributions from 2 particle states. But it will, for example, get contributions from 2 particle states once their anomalous dimensions get big enough.
But
did that answer your question?
My question was about the spin. If the spin of the light, I mean the lightest, the way you define delta gap, is it relevant here, or is it just the light?
No, it's not relevant. Let's see. Yeah, it's not the spin of the particle that saturates this delta gap is not important for this.
Thank you.
Thanks. Okay. Other questions? Okay, good. So now we'd like to understand what these sum rules measure. So we have some machine for generating sum rules, and they have some of the properties we want, but we need to choose the right ones. To understand that, it's useful to go back to flat space and ask this question about the flat space functionals that we thought we knew very well. There's sort of two ways to think about the geometry of a scattering process. One is that you can send in wave packets that are carefully cooked up to have to focus on certain physics. And that's something that there's been lots of work on in the context of AdS CFT. But there's another point of view that's closely related, but is a very useful, very clean point of view, which is to think about characterizing the geometry of a scattering process using the quantum numbers of intermediate states. So the way that works is, suppose you have, let's think about flat space. Let's suppose you have a 2-to-2 scattering process, and you have a pair of particles coming in, each with energy m/2. So these particles create an intermediate state with mass m. And suppose that the intermediate state has angular momentum j. Then basically from this diagram, we can deduce what impact parameter they must have scattered at. The impact parameter b associated with angular momentum j and these masses satisfies this equation. So we can rewrite it like this: b is 2j/m. So this gives us a way of keeping track of the dependence on impact parameter in our sum rule, just using the quantum numbers of the intermediate states. And this way of thinking about the geometry of the scattering process is equivalent to thinking about wave packets. Hold on a second. Okay, so this way of thinking about the geometry is equivalent to thinking about wave packets. And the way to see the equivalence is if you study the contribution of high energy states to our sum rule. So I called this C of m comma j. Maybe I'll scroll up a little bit just to orient you. So that was the thing that appeared inside the angle brackets in the sum rule. So it's this quantity. So it's a Geigenbauer polynomial here in the numerator with some, that's a function of the scattering angle. It has the subtraction in the denominator. So if we study that quantity in this limit of large M and large J, then it simplifies and it becomes equal to a Bessel function with some momentum P, where P is, where U is minus P squared, and B is precisely this combination of J and M. So by looking at the large M limit with fixed B, we can see that P is Fourier conjugate to B. So this Bessel function is just the average of a plane wave over angles. So this gives a way of taking a sum rule and figuring out what it measures without having to understand the wave packets that went into writing it down. This is going to be an extremely useful tool for us. So let's do the analogous thing in AdS. We can ask in AdS, if we have an intermediate state with dimension delta and angular momentum j, then what is the impact parameter at which the two particles must have scattered? And that's an exercise in classical mechanics in AdS space. And the answer turns out to be that the impact parameter beta, so this is the geodesic distance between the two particles. So by the way, I should say that in this case, in AdS, what used to be the transverse RD-2 has now become a transverse HD-1. Yeah, I guess this is a little d. So this is, I'll use capital D for bulk dimensions and little d for the boundary dimensions. So we have a hyperbolic space, and the impact parameter is now the geodesic distance between the two particles, and it's given by this combination of delta and J. And by the way, well, okay, I'll make that comment in a second. So this gives us an expression for the effective impact parameter of a heavy state. And similarly, we can write down the mass of a heavy state. So this is maybe a more familiar expression. At least this will be my definition. This then gives us a handle on the geometry of the bulk. And so we can identify two interesting regimes already. One is the Reggie regime, which is fixed impact parameter scattering. And that corresponds to looking at contributions of intermediate states with large dimension and fixed beta. And another interesting regime for us is the bulk point regime, which is large dimension with fixed J. So in the bulk point regime, when delta is large and J is fixed, then this becomes approximately equal to 2J over delta, which is like this B flat that I talked about before. So if we look at contributions of intermediate states in this regime, then we're looking at flat space physics. Now, what we had before in flat space was some rule that was Fourier conjugate to this impact parameter little b. And we want the same thing in AdS. And in particular, as I mentioned before, in order to run these constructions of getting positivity bounds on EFTs, we need access to large transverse momentum. So we want the analog of that. This large transverse momentum lets us focus down on short distances in the transverse space. And so in this case, the analog in CFT is we want something on the right-hand side that is like a Bessel function except for hyperbolic space. So we would like to find a sum rule such that the limit of the heavy action of the sum rule, so the action of the sum rule on heavy blocks at fixed beta, is equal to this to a harmonic function on HD minus 1, which is a Gegenbauer function. And as an example of this Gegenbauer function, for example, you could think about a 4-dimensional CFT, and then the Gegenbauer function is just proportional to a sine. So it's this oscillatory thing, and you should think of nu as being like, yeah, I already wrote it here, nu as being like transverse momentum. So nu is kind of like P. So nu is like P, and basically this is just the hyperbolic version of the Bessel function that we had before. Okay, so this gives us a target. So now we have a machine for constructing these dispersive sum rules. We know how to include subtractions, and now we have a strong condition on that we want the sum rule to satisfy, namely its action on heavy blocks, and this limit has to have this form. These turn out to be highly constraining, and they'll let us pinpoint the sum rules that we need. So any questions?
David, what's the definition of nu in terms of the quantum numbers on the left? So
good. We're going to have, yeah, good. So we're going to have a sum rule omega that depends on nu. So this omega is going to be something ck nu. So it's going to have two labels. One is the subtraction order or Reggie spin k, and one is nu, the momentum. Other questions?
Yep, sorry, I have one quick question. So this Reg limit is the Reg limit of the CFT, right?
Yeah, so I'm going to use, I'll probably use the words Reggie limit to describe two different things, but they're related. One notion of Reggie limit is it's a limit, a kinematic limit for the 4-point function where you move the points in a particular way. And I'll also use the word Reggie limit to refer to this regime of the heavy spectrum. And by the way, I should comment that this identification of geometry in terms of quantum numbers, I really should have had a citation here. It goes back to work by Joao and collaborators many years ago who understood the meaning of these quantum numbers in this limit and the connection to the Reggie limit in for CFT correlators.
I see. I'm just a bit confused about, like, if we take the bulk point limit at first, then we will get flat space S matrix, and then we take the Reg limit of that S matrix. Is this somehow related to, directionally related to the CFT Reg limit?
Good. So I guess your one point is that we're always going to be staying in what I would call Rindler kinematics. So where you have two pairs of points and they're space-like, they're time-like from each other, but space-like separate. Sorry, they're each one is time-like from its partner, but they're space-like separated from each other. So basically the kinematics here. That is not the same kinematics as what Sasha and Juan and I called the bulk point limit of the CFT correlator. And so it's actually important that we're not going to be going to that kinematics, but we're going to remain with this causal configuration. The reason it's important in this case is because we need this causal configuration to get a good sum rule, because the fact that 1 and 3, so I should have labeled the points here, but this is 1 and this is 3. So the fact that they're space-like separated is the thing that we need in order to get a sum rule, that their commutator vanishes. So the interesting thing is that we'll find a connection to the S matrix even staying within this this kinematic regime. So when I talk about the bulk point, when I say bulk point in this talk, I'm going to be referring to just this regime of quantum numbers, basically. I'm not going to be going to the regime of cross ratios corresponding to the bulk point limit, at least not explicitly.
I see, thanks.
Other questions? Okay, great. So, okay, so we have this condition, and this condition requires us to understand sort of in some detail how our sum rule acts on heavy blocks. So that's sort of the main computation I want to describe in this talk, because from this bit of technology we get most of the results that we need. So let's talk about computing the action on heavy blocks of these functionals. I described the functional as a double integral of the 4-point function against some kernel, and you can go to cross ratio space in this integral. So you just do a change of variables so that the integral, you express the integral as being an integral over cross ratios. And if you apply this integral to a conformal block, there's going to be a sine squared factor coming from the double discontinuity. So in practice, you have a double contour integral over z and z bar, and they're both going to wrap this S channel cut, and that gives you this sine squared factor. So I'm going to pull the sine squared factor out and bring it to the left-hand side and talk about the rest. And so the rest is just the integral over cross ratios of some kernel omega. And we would like to understand how to compute these integrals, where the kernel multiplies an S channel conformal block. Okay, any questions about this expression? Okay, so whenever you have an integral over cross ratios, you should think about whether it would be simpler to think about it in position space again. So I know we started in position space, but we had a very particular integral in position space where the ingredients in the integral didn't have nice conformal transformation properties. But by going to cross ratios and then lifting back up to position space, we effectively do the integral over all the orbits of the conformal group, and we get a nicer integral. So let's go back to position space. We have an integral over cross ratios, but we can lift that up to position space, and then it becomes a nice conformally invariant integral. So this is an integral over all 4 positions, modulo the simultaneous action of the conformal group on all of these 4 positions. And the idea is that it's maybe easier to understand going from this expression to this expression. Basically what you do is you gauge fix the integral. And the gauge fixing that you need to go from here to here is the standard fixing of the conformal group that we do when we talk about 4-point functions. We put 4 points on the same plane, and then z and z bar, and we put 3 of them at 0, 1, and infinity, and z and z bar label the position of the 4th point. So if you do that gauge fixing, you end up with this expression. And so that lets you then lift to this expression. So we have the integral of our kernel, a conformally invariant integral of our kernel against the conformal block. The key trick is to use the shadow representation for the conformal block. So the integral is over this causal configuration where 1 is in the future of 2 and 4 is in the future of 3. And we can write this conformal block as an integral of a product of two 3-point functions, where one of the this fifth point that we introduce is integrated over a diamond. And I could have chosen the diamond to be this one instead. It doesn't matter. And I'll just choose conventions where we're integrating between 3 and 4. Okay, so now we have, we've seemingly made life even worse. We now have a conformally invariant 5-point integral of a product of our kernel. But the nice thing is that it multiplies now something a little less mysterious, which are these products of 3-point functions. Now, the reason that these integrals are hard is that conformal blocks are complicated. And so specifically, the x5 integral is complicated. And the trick is to not do the x5 integral. We don't like it, so let's not do it. And so we'll choose a different gauge fixing of this integral that freezes x5 so that we don't integrate over it anymore. As I said before, the integral over cross ratios was a choice of gauge that froze 3 of the external points at 0, 1, and infinity and integrated over the 4th point. Here, we're going to freeze this new auxiliary x5, and we're going to set the external points to have some relationship to each other, but they're still going to be integrated over. The conformal frame that turns out to be nicest for this problem is to, so as I said, fix x5. So we're going to fix it to be at the position of a time-length unit vector e. And then 1 and 2 and 3 and 4 are going to be in this kind of symmetric configuration around the Reggie limit, the U-channel Reggie limit. So this is a pair of Rindler wedges. And 1 and 3 are displaced by the same amount away from the Reggie limit, and so are 4 and 2. And these are, this configuration is labeled by this pair of future pointing vectors in Minkowski space. And the claim is that the sort of amount of symmetries that you use to do this gauge fixing is you have enough symmetries in the conformal group. And just to get an intuition for that, the idea is that 4 and 2 are kind of symmetric around this point and its neighbor in the next point gray patch. And 1 and 3 are symmetric around this point. So the amount of gauge fixing you're doing is kind of like fixing 3 points. You have to fix this point, and this point. And so it's like a 3-point function worth of fixing. So we know you can use the conformal group to fix 3 points to wherever you want. In this case, we're fixing x5, and then we're fixing this sort of symmetric point between 2 and 4 to be one thing, and the symmetric point between 1 and 3 to be something else. So this is an alternative gauge fixing, and it leads to a nice expression for what before looked pretty complicated. So we now have an integral over x and y of our kernel times some function which is just a product of 3-point functions. So the scary conformal block has gone away, and now we just have some elementary factors. Okay, so now it's straightforward to study the action on heavy blocks. We can just take the large delta and j limit of this product of 3-point functions. And a nice thing that happens is that in this limit, they just become exponentials. So specifically, the idea is that the conformal block at large dimension, 1 and 2 get pushed away from each other, right? The conformal block is highly suppressed when 1 and 2 are close together, so they're getting pushed in this direction. And that's what this exponential factor is doing. And here these vectors p and p bar appearing in the exponential are just written in terms of the quantum numbers. So what pops out of this is that in the large dimension and large j limit, you get that the action on heavy blocks is just the Laplace transform of the kernel omega. This Laplace transform has appeared before in the impact parameter representation for conformal blocks. One thing about this is, so that was motivated from this sort of wave packet picture of setting up correlators where you pick wave packets in a particularly nice way. And here it kind of pops out of thinking of the action of functionals on heavy blocks. And one nice thing about this point of view is that it's straightforward to go beyond this large delta and J limit. You just have to keep all the structure in these 3-point functions. Okay, so any questions about this? Okay, so good. So now we have enough of a view that we can aim for the target. So what we wanted was a particular form for the action of the sum rule on heavy blocks. So it was this expression here. So we wanted to get this Geigenbauer function, this harmonic function in the numerator, and some power of m in the denominator. And the way to get that from this picture is to think about this Laplace transform. Basically, the Laplace transform takes Geigenbauers to Geigenbauers. I'll explain that in a moment. So if we consider a kernel omega whose leading behavior in the Regge limit looks like this, it's just a power of these. So the Regge limit is little x and little y go to 0 in this in these conventions. So if it's just a power of this small parameter times Geigenbauer of the angle, then when we do the Laplace transform, we get back exactly what we want. So we have these combinations of p's and p bars, and that becomes exactly the expression we want. Times some product of gamma functions that I won't write explicitly here. And so what we need to do then is just start with a kernel where we divide by this product of gamma functions. So I took this factor, let's put it in the denominator instead, and have the leading behavior of the kernel in the Regge limit be this. And then that gives us exactly what we want for the action heavy blocks in the Regge limit. So that's the trick. And let me give a little bit of interpretation here to sort of explain what's going on. So the Regge limit is this limit that x and y go to 0. And the stabilizer group of the Regge limit is SO11 cross the Lorentz group. So this SO11 basically takes you towards and away from the Regge limit. It parameterizes how much, hold on a second. Okay, it parameterizes how close these points are to the tips of these Rindler wedges. So that's the SO11. The Lorentz group acts on these two vectors, x and y. And so it sort of changes the angle of approach to the Regge limit. But this exact same Lorentz group is the isometry group of the transverse hyperbolic space. So the fact that the same Lorentz group, that we understand the action of the same Lorentz group on the boundary and in the bulk gives us the connection that we need to construct the dictionary. And the idea is then to project onto irreducible representations of this Lorentz group. And if we do that on the boundary, then that also projects onto irreps in the bulk. If we go back, that's what's happening here. This Geigenbauer transforms in an irreducible representation of the Lorentz group, acting on little x and little y, and the representation is labeled by a weight nu. And by sticking in this Geigenbauer, we get back the same Geigenbauer with the same weight. And the effect of the bulk is basically to introduce this factor gamma of nu. And because gamma depends only on the weight of the representation, that means that gamma represents a kind of Lorentz invariant kernel. So this gamma of nu is a Lorentz invariant kernel that blurs the bulk as seen by the boundary. And then all we need to do is divide by this gamma of nu squared, and that's sort of undoing the blurring and focusing into the bulk. Any questions?
Is there a problem with convergence when you divide, because this function now will probably grow at large nu?
Yeah, that's a great question. So you're right. So when you divide by this gamma of nu, you need to. It's important to keep track of. The sum rules that we get will be distributions in nu that need to be paired with some kind of test function. And when you divide by this factor, it changes the family of test functions that it can be paired with. And it's important to keep track of that.
Thank you.
Other questions? Okay. All right. So now we understand the CFT versions of these different properties that we wanted dispersion relations to satisfy, and we can put them together and ask for the sum rule that satisfies these properties. And an example of a sum rule that has all of these ingredients in it is what I'll call C2 nu, and it's equivalent to the Lorentzian inversion formula at a negative spin. So that is related to this double integral over null lines. There's a subtraction factor 1 over uv, which is meromorphic. It has poles at the S and T channel of the E limits. And we also divide by this factor here in order to achieve bulk focusing. I emphasized one way of deriving this C2 nu functional, but there are other nice ways to do it, and it has nice expressions in null and space, for example, that I won't have time to talk about. So this is the CFT sum rule that will play the role of a spin 2 sum rule, spin 2 dispersion relation, and there are more general CK nus that play the role of higher dispersion relations. Okay, so now that we have the sum rule, we're almost there to a dispersion relation in the flat space limit. So the sum rule by construction has this property that it basically measures something with some fixed transverse momentum in hyperbolic space in the Regge regime. And now one can ask for the action of the sum rule in the bulk point regime. So remember, bulk point regime was large delta with fixed J. We already have, I have already described the technology that you need in order to evaluate the functional in this regime. I'll scroll up. So it starts again from this expression for the action of the functional. And instead of simplifying these T factors to an exponential, you just need to keep the exact expression here and look at the behavior of this integral in the bulk point regime. So this expression is exact, and so you can use it to figure out the behavior of the integral. And an interesting thing happens in this calculation, which is that so the answer turns out to be this, and this is precisely the heavy density that appeared in flat space dispersion relations. So this is flat space physics popping out of this. The way this works is that in this regime, the integral over little x and little y is controlled by a saddle point. And this saddle point is kind of interesting. So remember, this is our configuration. We had little x here and little y here. And if we go to light cone coordinates, the saddle point is at imaginary positions for the light cone coordinates of both x and y. The physical interpretation of this is that these imaginary light cone coordinates are indicating a kind of double whip rotation. So we started with this configuration where space goes this way and time goes this way. And after this double whip rotation, they're being exchanged. And why is that interesting? Well, let's see. Forgot my labeling here, but it doesn't really matter. The reason that's interesting is because by exchanging time and space, allowing time to go this way, It means that we're in a causal scattering configuration in going sideways. So remember I said that it was important for our sum rules to remain in this sort of Rindler configuration where we don't go near the bulk point regime of the cross ratios. But with this double whip rotation, now this pair of operators becomes time-like from this pair of operators, and it looks more like a scattering process. So the idea is that we don't study CFT correlators in this. We don't put the external operators in this complex kinematics. Instead, the complex kinematics pops out as a saddle point of an integral over Rindler kinematics with an appropriate weight. And so we call this phenomenon space-like scattering. The idea that you can probe at least moments of the S matrix from within the Rindler regime. And this is important for us to be able to make rigorous statements, but also get these this bulk point physics to pop out. Any questions? Okay. So this is the right-hand side of our sum rule. So we see now that the right-hand side of the sum rule is going to have angle brackets, and in the angle brackets, there's going to be this, at least for the contribution of states in the bulk point regime. The left-hand side of the sum rule, I don't have time to talk about, but you can evaluate the contribution of light states to these sum rules, and it turns out to also agree with flat space dispersion relations in an appropriate limit. The idea is that if you compute the contribution of light states, then you get what would appear in a flat space dispersion relation plus corrections at large nu. And these, we're going to be interested in studying physics at large transverse momentum. So these large nu corrections are going to turn into 1 over delta gap corrections. So as an example, if you compute the contribution from light states to this C2 nu sum rule that I described, there's a contribution from gravity, and it looks a lot like flat space. So in flat space, we had 8 pi g over p squared plus 2g2 plus g3 p squared plus ... And here it's similar. In AdS, the contribution of the graviton propagator is modified. So this is a new contribution in AdS. And another thing that happens is that the series of corrections that you get here include extra terms because of the AdS curvature. So in general, the structure is that you get what you would get in flat space plus what will turn out to be 1 over r AdS corrections. So feel free to ask questions about that, but I won't have time to describe the calculation in detail. So in fact, I'm basically out of time, so I'm going to go really fast over this part. So now we have sum rules that become flat space dispersion relations, and then the idea is to construct positive sum rules by using flat space technology. So here I'll follow the strategy from this paper. So the idea is to start with your dispersion relations and construct a so-called improved dispersion relation that measures a finite set of bulk contact interactions. In fact, in the CFT case, these improved dispersion relations aren't quite as improved as they are in flat space. And we can talk about that more if you like, but this is the combination that you would get by just analogy from flat space. And then you use your favorite numerics or analytics or whatever to construct a flat space functional that's positive. So let's suppose someone hands you a flat space functional, which is an integral of some wave function f of p against this the flat space version of this improved sum rule. So in this previous paper, we described how to construct positive functionals of this form. So let's suppose you have such a thing. Then the idea is to apply a very simple dictionary. The dictionary is that you write p equals nu and m equals delta gap. And you take the flat space sum rule, which was curly c to u, and you replace it with non-curly c to nu. And when you do that, you get a new you get a CFT functional omega AdS. And the claim is that if omega flat is positive, then omega AdS is positive, possibly after some small modification. That's the claim. And the idea, the reason for this claim is that positivity in the bulk point regime. So when we have this functional omega AdS, we need to check whether it's positive as a function of delta and j. And so now we can talk about the different regimes of delta and j. Positivity in the bulk point regime is guaranteed by the agreement with omega flat. So that's just automatic. But you have to check. There is something non-trivial to check, which is positivity away from the bulk point regime. So we can draw the heavy spectrum. We have delta, we have j, and the bulk point regime is some regime of small j over delta. Everything here is everything there is positive automatically, but you have to check positivity out here in the Reggie regime. Sometimes you get automatic positivity in the Reggie regime, and sometimes you don't. But when you don't, you can just wiggle this f function a little bit to achieve positivity there. So the claim then is that this is a machine for taking positive functionals in flat space and producing positive functionals in CFT. And once you have a positive functional, it immediately gives you a bound on low energy physics. So this gives an infinite series of bounds on low energy AdS CFTs. Okay, so now there's the question of the interpretation of these bounds. Here we have what I think is a reasonable story, but there's definitely room to improve it. So the light side of these dispersion relations agrees with flat space up to these 1/nu corrections that I talked about, these corrections from the AdS curvature. The effect of this is that, so you have these positivity bounds, and on one side of the positivity bounds are exactly what you would expect from flat space. So for example, here would be some linear combination of 8 pi g times some number plus delta gap squared times g2 plus delta gap to the 4th times g3. And you know that all of this is greater than or equal to 0 if you have a positive functional. So this is great. This is exactly the kind of thing that we want. We want bounds that say that these kinds of combinations are greater than or equal to 0. But there are additional corrections coming from the AdS curvature. And these corrections are self-consistently suppressed by delta gap squared. So if you know that all of these g sub n's satisfy two-sided bounds, then those two-sided bounds imply that all of these corrections, all of these extra things are tiny. So what you really get is a kind of statement, kind of like a Bootstrap island, where if you are sufficiently close to a bulk effective field theory, then you have to lie inside the EFT island. But you can have different notions of closeness. So one thing that would be nice is to so basically what one has to ask about is the distinction between the EFT island and the other region out here. So in Bootstrap language, it's this kind of situation. And in the case of the 3D icing model, there's an island and then there's another region, and the separation between the island and the other region is easily quantifiable. In this case, there's I think an interesting question to maximize the separation between these the EFT island and the other region. So I want to point that out to be perfectly honest with all of you, because you guys probably have a great chance of sorting this out. Okay, so I'm way over time. Let me just end with some points for discussion. So from this construction, you find that a huge class of bounds from flat space apply in AdS. And a nice thing about this is that the only assumption really is the usual CFT axioms. In particular, all of this is coming from causality of the boundary theory. It would be nice to improve on this question about controlling these self-consistently small corrections. So that I think it's a technical point, but it's an interesting one to think about. Okay, so one interesting thing I didn't have time to talk about is that if you try to write down dispersive bounds in four-dimensional Minkowski space, you run into IR problems in gravitational theories. And AdS4, interestingly, fixes these IR problems. So you actually get non-trivial bounds in AdS4 that almost look like what you want. So for example, there's a bound on G2 that says it's bigger than G Newton over delta gap squared, but there's an extra log delta gap factor that basically comes from the fact that the IR divergence in flat space is cut off at the AdS radius. So this is almost like CFT dimensional analysis, but not quite. There's this extra log there. So it's interesting to ask, can we do better? Can we get rid of the logarithm? And I think that getting rid of the logarithm probably will require understanding these IR divergences in flat space better. So if you could come up with an intrinsically flat space mechanism for getting rid of the IR divergence, then it should get rid of the logarithm of these bounds. But it is interesting that AdS provides a nice regulator for these IR divergences. So another thing is that maybe a surprising result of all of this is that the bounds on AdS theories that we get are the same as the flat space bounds, at least in large delta gap limit. So you may have expected that that bounds in AdS would somehow be different. And so far, the reason is that these bounds all come from studying very small impact parameter scattering. And therefore, it's maybe not surprising that they're the same in flat space and AdS. The non-trivial place where AdS came in was, if we look back here, checking positivity. You remember that positivity here was guaranteed in the bulk point regime, but positivity out here was not. But it turns out we can always add something to fix positivity in the question mark regime. So it was a place where there could have been a difference with AdS and flat space, but it didn't seem to happen, at least not in the examples that we studied. But it could happen. So maybe you could imagine a slightly different construction of functionals that do show a difference between AdS and flat space. So I think it's an interesting question. Are there new bounds that are stronger in AdS in certain ways or weaker in certain ways? Can you have differences in bounds that are sensitive to the global structure of the space-time? Another question is, where is string theory? So in the numerical flat space bounds on gravitational theories that have been computed so far, you get interesting bounds on, say, G2 and G3. So we have G3 and G2, and there's some allowed region, and there's an interesting extremal point, but the extremal point doesn't look anything like string theory. And so this is an interesting question in both the context of AdS and in flat space. How do we get bounds that are saturated by weakly coupled string theory or strongly coupled string theory? I think this is an extremely important question. I mean, if we could achieve this dream of having optimal bounds and theories that satisfy the bounds, then that would really be the Bootstrap dream. And another general question is about this phenomenon of space-like scattering, this fact that you can stay within the Rindler regime and measure properties of the S matrix. It's interesting to ask whether this trick has other applications. So I'll stop there. Thanks a lot.
Thank you. More questions for David.
Hey, David.
Hi.
I want to, well, first say thanks a lot for the nice talk. And I want to follow up a bit on Joao's point. So the fact that the spin dependence of delta gap is not a part of your analysis, to me suggests that there's something missing in proving what HPPS really wanted to tell us. But someone else might say, well, actually, we are maybe missing something. And, you know, perhaps there's a heretical suggestion that one needs to augment the HPPS minimalist conjecture with some other statement about about the scalar sector of holographic CFTs, but I think there's not great reason to think that, but all this sheds light on how scalars are hard to access using the methods that we're used to using in the Bootstrap context. So I guess my question is, if you, well, I'd be curious to hear people's thoughts on this, but also if you did this analysis in a gravitational theory, do you think that that would be good enough to overcome this issue? Or is there something more inherent with the technique that even adding external spin wouldn't fix?
Let's see. So the issue, yeah, let me see if I can understand the issue a little better. So let's see. Yeah, I don't quite understand. So what is the goal that one wants to aim for?
So I think the goal one wants to aim for, and P is here, so P can speak his mind. But the goal one wants to aim for is that showing that large N and large higher spin gap is enough for what we want to show about holographic CFTs being dual to AdS EFTs. And the fact that it's a higher spin gap is central to that, and that was part of the power of chems, because only higher spins could fix that problem. In this case, it's not true that only higher spins can fix the problem as far as things have been set up. And so we want to ask,
well,
are we supposed to be able to do better, or is there some physics there?
Okay, so I guess one comment is that if you add scalars, then scalar exchanges don't contribute to these sum rules.
Right.
So another comment is that if you add, say, spin 2 operators, then they do contribute to the sum rules, but you still get valid sum rules. So I'm not sure what the statement is. I think we should ask what the statement is supposed to be. So yeah, it's not obvious to me whether we should expect additional sum rules. Maybe we should ask this question in flat space. Should we expect there to exist additional sum rules besides dispersion relations that that give stronger results on spin 0 particles? I think it's an interesting question, but I think it's already a flat space question.
I think, well, yeah, there's an analogy to flat space that we could use to guide our thinking, but I think the thing that we've been shooting for a while is just to show that one doesn't need any more assumptions beyond those that HPPS said are required. And so we want to put that in the sharpest relief. And so it seems plausible that if you try to constrain 4-point interactions of gravitons, not scalars, maybe the spin sensitivity helps you there.
Let's see.
Sorry, but at some level, if you take HPPS completely at face value, I think they meant, I don't think we should nail them to the exact words that they said. I think they made a conceptual claim more than a precise claim. So for example, isn't already having KK modes in some sense an obvious counterexample? The theory is not if I have KK modes, the theory is not local in 5 dimensions, it's only local in 10 dimensions. So
yes, indeed, but
so that's a counterexample to HPPS.
Local theory.
But trivial
no. I never thought of that as a counterexample, because they don't say in what dimension the theory has to be local. There is some dimension which is local, and then we can talk about the density of
interpretation. Yes, but
I think that's been the prevailing interpretation for a while. So I want to, now that we're in an age of more precise tools, I think it's especially important to ask the precise questions.
I don't think our priors are clear, right? All the holographic examples that we have under control are such that automatically higher spin comes in the same multiplet with, say, spin 2 or even spin 0. So most of all examples that we have, the question is sort of irrelevant. And so the question is whether there is some hypothetical large N sequence of purely bosonic, perhaps, or perhaps N = 1 CFTs where necessarily this scalar and spin2 states come at the heavy states come at the same scale as the higher spin, or perhaps there is an intermediate scale where you have spin 0 and spin 2.
Yes.
Hard to know. For me, it's hard to know what to imagine, right? I mean, who knows? I think that was, is that what we're getting to?
That is definitely a version of this question. Yeah. I mean, you could imagine that we're imagining a setting with no supersymmetry, and where actually there is an extra statement that must be made about the way the scalars participate in these holographic limits compared to the spinning operators. And this is reflected in the fact that, you know, the scalars don't give divergent contributions in Rege limits and so on. So I think that's exactly the kind of setting where we want to think about what we should say. The original version of HPPS, I think, had that in mind, of course, as evidenced by their examples, but we maybe now want to ask more refined questions.
Yeah, I think I'll just reiterate the comment that I think that it's useful to split these questions into questions that can be phrased and addressed in flat space, and questions that require going beyond having some difference between AdS and flat space. So here is a machine for importing flat space bounds into AdS, and so yeah, I don't know the complete answers to your question, but I think it's a useful way to frame the question.
I'd be curious maybe to ask if P has any comment on what he thinks.
I agree with David that, for example, this question, both of your questions could be done in flat space, right? We still did not, I don't think anyone applied this more recent effective field theory as a theorem technology to gravitational scattering, right? Even at tree level, people only basically did external scalars. So we can ask the same question there. What will be the relevant mass gap that will control the bounds? Will be the spin 2 mass gap? Will be the spin 0 mass gap? Even in
the paper by Sasha and Zvi and others had some gravitational scattering.
Yeah. So well, one obvious difference is that when you have external gravitons, is that scalars contribute to some roles, but they couple non-minimally, and so you definitely constrain these couplings. But presumably, what Eric has in mind is more like constraining one loop scalar boxes where we have minimally coupled scalars, but there can be some many of them, like lots of say light scalars, and we know, and this is also related to comment about flat space. In flat space, we can bound the number of scalars coupled to graviton, or at least related to some breakdown of effective field theory, by using the conditions that, you know, partial waves are less than 1, because otherwise, if there are too many of them, they all contribute positively to the partial wave, and they will violate at some energies that partial wave is less than 1. So either, let's say, and in AdS we also, and it's related to this other compact dimensions. So if we have some extra states, some Kaluzi-Klein modes, they will show up at one loop. And so, do you have an analog of this, you know, partial wave absolute value less than 1 in AdS? Do you see the analog of that?
Yeah, I mean the analog of an analog of that was already explored by Simone. The statement that d-disk is less than 1.
But actually, yeah, I wanted to ask you, I'm confused by that, because I thought we also, you know, with you, we had this issue of outliers where you know that asymptotically bounded by 1, but
yeah, that's right. Yeah, so that's what I was going to say. Like, it's not clear how to make use of information like that. At least, but I would say that the outliers issue is solved by is partly solved by this technology. So the outliers issue was the problem there was that if you try to think about just the Lorentzian inversion formula, which is what we were thinking about before, you can ask, let's say you're interested in, you want some kind of bound on the d-disk and the Regge limit. And the Lorentzian inversion formula gives you a statement that the integral of the d-disk of G, let's say, contributes to the stress tensor pole. So the integral of the d-disk of G times some special kernel gives you 1 over CT times 1 over delta minus D. And you want to use this to deduce properties of the d-disk. And then once you have properties of the d-disk, you want to figure out what those imply for other things. So this is the strategy that Simon was using in the Lorentzian inversion formula paper. So he was saying, okay, so we have the d-disk and we can plot it as we approach the Regge limit, and it has to be positive and bounded, and it has to contribute to the stress tensor pole. So we know it has to have some kind of shape like this, and from this you want to deduce things about bulk couplings. Am I making sense?
Yeah, well,
Good.
yes, so I'll continue.
So I just wanted to say that the problem was that in the inversion formula, the thing that you're able to measure are these poles,
Yeah.
which come from the deep asymptotics of the inversion integral.
That's
So you
right.
only ever learn about asymptotics of the d-disk. You don't learn about its finite, its value at finite cross ratios. These dispersive bounds do constrain its value at finite cross ratios. Because the right-hand side of the dispersive bounds is not a pole, is not something that's becoming infinite. It's something finite. So they give you an infinite set of bounds on the d-disk. The problem about d-disk less than 1 is there you're asking for a bound. So the bounds that I was talking about are all spin 2 or higher convergent bounds. So basically they're taking the d-disk and convolving with something that decays sufficiently quickly as you go. So this is the Regge limit that way.
Mhm.
So you're convolving with something that decays sufficiently quickly. The d-disk less than 1 bounds would be relevant only if you don't suppress this Regge regime as much and you try to convolve with something like this. At least naively, I think this would require something like a spin 1 dispersion relation and understanding how that behaves. But we don't have any of those.
Maybe if I quickly follow up. So if you, let's say you assume this shape for the disks that you just drew,
Yeah.
will it get rid of this technical assumptions that you made one slide before? Will it take care of it? So you had to assume something and say, if you assume this natural shape for the disk, can you show that this always holds?
That's an interesting question. So you're saying, okay, so what we know are we have a whole bunch of information about the moments of d-disk, and you're saying if you write down an ansatz for a nice function that has those moments, does that imply what you need? Yeah, I don't know. That's an interesting question.
I suggest we move on to other questions. Shungi
Yeah.
is waiting for a very long time. Go ahead.
Yes, well, thanks for a wonderful talk. I have 2 questions. Maybe you can help me. First question is, since you mentioned about string theory, we know if you do string theory, you can improve the sharpened asymptotic bounds. So for instance, in terms of the stress energy exchange will be lowered. So in terms of language of Regge, the intercept will be below 2. Would that help you for something for your sum rule?
Let's see. That's an interesting question. So that is the mechanism by which weakly coupled string theory satisfies these spin 2 dispersion relations.
So if you have intercept below 2, so you get a slightly better convergence.
Yeah. Yeah, so the dispersion relations that these dispersive sum rules that I was writing down, they're labeled by this this subtraction level k, which is an even integer, and you could have odd integers if you considered, you know, non-identical particles, but it doesn't. But yeah, it doesn't seem like we can write down a fractional spin dispersion relation, which would be the kind of thing that you would need to take advantage of that extra difference between spin 2 and lower. But I think that, yeah, this is an important question. It may be very related to this, you know, where is string theory question. You know, what kind of mileage can we get if a theory doesn't saturate the chaos bound but is a finite distance away? Yeah. That's a really interesting question.
If I ask a very quick question to just have clarification on your statement about space-like scattering, are you, for instance, if I'm talking about 4-point function of 4 currents in the Minkowski setting, then each current is space-like, okay? Is that what you're talking about? Because that fits into the configuration of sort of pairwise Rindler wedge. Are you talking about something different?
Well, the thing I'm talking about, it would work for current insertions. The idea is that you can measure moments of the S matrix, that is the things that enter dispersion relations, by staying within Rindler kinematics and just smearing the points appropriately. Yeah. So
it is the ordinary scattering of equivalent of, say, 4 space-like currents.
Yeah, you're asking, could you study photon scattering?
So are you talking about that, or talking about something different when you say space-like scatter?
I guess maybe I'm not precisely gathering what you have in mind. I just mean that basically the phenomenon I'm talking about is that there's a singularity in causal kinematics from a scattering process, and the idea is to probe that singularity not by going to it, but by injecting this transverse momentum that pushes the saddle point towards the singularity. So I guess it's kind of, I think it's kind of similar. There was a nice paper by Maldacena and a student about probing the black hole singularity using thermal expectation values. And it was a kind of similar idea that the singularity leads to saddle points in certain integrals. The presence of the singularity, you know, saddle points are attracted to the singularity. And so by looking at the right extreme regime of a boundary observable, you could find something that that went close to the singularity in the bulk.
Is this effectively in the string theory? You go to the fixed angle scattering, find out everything's dominated by saddle points, which is.
So this is not fixed angle scattering. This is well, I mean, in the end, you sort of indirectly learn something about fixed angle scattering, but you're not going to fixed angle scattering kinematics.
Okay, thanks.
Sure.
Walt, I think you're next.
Yeah. I just had a question whether you have something to say about effective field theories in AdS without gravity.
Without gravity.
What happens if you switch off gravity?
Yeah, so if you switch off gravity, it makes things a little simpler. Let me scroll up here. So if you look at the light contribution to these sum rules, so I wrote it here. So the contribution of gravity is here. And the main effect of this is that you should think of this as being, morally speaking, a singularity as nu goes to 0. It's not actually singular because it's cut off by the AdS radius, but it's morally singular because if you try to integrate this against some function of nu, then if that integral is sensitive to small nu, then you don't get good EFT scaling for the integral. I don't know if that makes sense, but so the presence of this term restricts the kinds of sum rules you can study just the same way as the presence of the graviton pole restricts the sum rules you can study in flat space. So if you are interested in non-gravitational theories, you can just drop this term. And then things become a bit technically simpler for the same reasons as in flat space. So in flat space, if you don't have gravity, then you can take derivatives around the forward limit. And now you can again take derivatives around the forward limit. And the nice thing is that in the non-gravitational case, those derivatives around the forward limit will give you good EFT scaling for your results. So yeah, so I think that as far as I know so far, the basic story would be that all the flat space bounds carry through to AdS, that bounds from the forward limit work in AdS.
I see. So it's that, and you don't get anything stronger than what you have in fact.
Yeah, I don't know how to get anything stronger, but it's an interesting question. So maybe I should make a comment about that. So there's this sort of regime of the spectrum where you have to study positivity, and as I said several times before, this part down here, the bulk point regime, positivity is automatic. And if you take flat space functionals and you translate them to AdS, then you can get positivity in this regime. But it's maybe more positivity than you actually need, because if you have a bound on the twist gap, then there's an upper bound on J. So actually there's a cutoff on the AdS impact parameter. And the functionals that you get using these constructions are positive above that cutoff. So it's interesting to ask whether you can relax positivity up there and get stronger bounds.
Right. And just as a reminder, the flat space bounds, I've seen bounds that all the G's are positive. Is there with the canonical scaling?
Yeah.
Is there more?
Yeah, absolutely. So there are two-sided bounds on all EFT couplings in flat space. They haven't all been computed, but huge classes of them have been computed. I think actually it's an interesting question what the asymptotics of those bounds are. I don't know if anyone has worked on that. I think Simone and Vincent did some numerical exploration and kind of guessed the asymptotics, but that would be interesting to know. But it certainly seems like there are two-sided bounds on everything.
I see. Thanks.
Sure.
Tom, go ahead.
Hi. So in the S matrix bounds, there was an assumption that it was weakly coupled or tree level. And
Yeah.
I just at a technical level, I sort of missed where that entered in the CFT argument. Was that in these comments on your last slide, or can you say more about where that came in?
Oh,
or?
yeah. So that was here in this light contributions thing. So the technical thing that happens to lead to this formula is
until this point, these sum rules could be applied to any CFT, right?
Yes. Yeah, that's right.
Sorry, go ahead. Yeah.
Yeah, so they could be applied to any CFT, and that's consistent with the idea for thinking about loop corrections to dispersion relations, which is that the dispersion relation gives you a true sum rule that does bound the low energy theory, but there's a question of interpreting that sum rule in terms of the couplings you see in the Lagrangian, and to do that interpretation, then you have to worry about whether your low energy theory is weakly coupled or not, and what the map is between the Lagrangian and whatever observables you're bound. So there's a similar thing here. You write down these sum rules. They are rigorously positive, and then you can ask, what do they bound? And the answer to what do they bound is much simpler if the low energy physics in the bulk is weakly coupled, and if it's tree level, then it leads to this formula. Otherwise, there will be loop corrections to it.
I see. Okay.
There is one more question by Murat.
Hi.
Hi.
You've alluded to finite temperature a couple times, I guess. So I wanted to ask about whether you've thought about that. I guess there's a couple maybe interesting things that I could think of. One is take this setup and try to take like two of the external operators to be heavy and try to make some connection to either finite temperature correlators or just black hole physics. And this space-like scattering thing could be, maybe there's something analogous like that to sort of probe either probe what's going on near a black hole, etc. I'm not sure how that would go, or just analogously take just study thermal dew-point function by itself and try to devise similar machinery. But I guess one interesting connection that's missing, which I've sort of partially thought about with Sasha at some point, is there's no sort of positivity, as you know, with in the thermal case. So is there some way to connect the dispersion relation here to the thermal one and get something sensible? I don't know if you've thought about any of these things.
These are interesting questions. I haven't thought too much about it. So yeah, if you were to take two of the operators to be heavy, it would definitely change the analysis. I think let's see. One would have to think carefully about how the large N expansion should work in that case. If you're interested in black hole physics, then you want to take two of the operators to be so heavy that they really modify the large N counting, and then that would modify, what. Yeah, I'm not sure how useful the D-disk would be if you just throw away large N counting. So yeah, so that I don't know the answer to that, but that seems to be a bit tricky. I mean, one comment, one thing you asked about the space-like scattering idea and probing black holes, I think it's almost the same thing as what was done in this paper by Maldacena, except they weren't looking at scattering; they were looking at one-point scattering off a black hole, basically. So yeah, so I think the answer is yeah, it could be useful. It's a kind of interesting way to secretly sneak a view at singularities in a kinematic regime that you wouldn't usually think you had access to. But yeah, maybe you could think about scattering in the context of a black hole, and if you could secretly see any interesting singularities there. Yeah. Let's see. Yeah, I'm not sure what else to say about the thermal case, though. I hope that maybe that answers some of your questions.
Well, thank you. It's very thought-provoking.
Okay, so we are 45 minutes over the official time. I don't know, are there still any other questions? Tom has his hand up, maybe just no. David, thank you very much for this nice talk and answering all these questions.
Okay, thank you all.
Thank you, David.
And see you tomorrow for day 2 of Bootstrap. Thank you.
Thanks, David.